Okay, this is to finish up the notes from section 3.2. We are doing some symmetry, graphing using a table of values, and the other piece was intercepts. So kind of just summarizing a few other examples we didn't get to in class. So I'm going to go ahead and go down to the examples because all of the notes part we covered. We did A and C in class, but we did not do B, so I'm going to talk about that one for a second. One of the first things that happens when you're dealing with these, when you're doing a table of values, sometimes it's easier if this is already factored to plug it in really quickly. So this would be an x minus 8 and an x plus 5. So then when we did our table of values, we made an XY chart. We found our intercepts by plugging in 0 to x one time and y for the other. To do the x being 0, it's actually easier to plug into this case because that would just be 0 squared minus 3 times 0 minus 40. That's a big y-intercept, or actually a very small one because it'd just be negative 40. So probably not going to be graphing that piece, but we at least found it. And then this one, when you're putting in 0 for y, this is why this is nice that this is factored, you see that this solves and you get x equals 8 and x equals negative 5. So you actually have two different x-intercepts. It's always good to get at least one more point, so sometimes I just plug in positive 1, just see what pops out. So this would be 1 squared minus 3 times 1 minus 40. This is probably going to be way too small because that would be 1 minus 3 minus 40. Yeah, so let's try... A good point to have is what we call the vertex, which would be halfway between positive 8 and negative 5, which I'm going to go ahead and plot over here. So there's negative 5, and there's positive 8. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 away from each other. So 1, 2, 3, 4, 5, 6.5. If you plug in 1.5, you'll actually get what we call the vertex. It'll be the either highest or lowest point of this picture. So if we do that, that would be, let's plug it into right here. 1.5 minus 8, 1.5 plus 5, that would be negative 6.5 times 6.5. So 6.5 squared, but it'll end up being negative, is negative 42.25. That's actually going to be the lowest point of the parabola. So I think we are going to have to change the way we've scaled this. Let's say that this is negative 5, negative 10. No, that's not going to be big enough. We may have to go by tens. So this would be, and these would change to 10, 20, 30, 40, 50, and negative 10, negative 20, negative 30, negative 40. Just changing the scale so we can actually plot some of these points. So 0, negative 40 is our y-intercept. So I guess we can label that now. And this is negative 5, 0. This is 8, 0. And then the lowest point was 1.5, negative 42.5. So in a parabola, there's always a lowest and a highest point, depending on if the parabola opens up or down. In this case, this one's opening up, so there's a lowest point, and that's always halfway between the two x-intercepts. So that's why I was doing that counting. And then this has a symmetry, but the symmetry is not a y-axis symmetry because the symmetry actually exists right there at that 1.5 value. So we do have to show the test though. So algebraically, our tests for symmetry, here's how they work. If you're doing the x-axis symmetry test, you take a y and change it to a negative y. So for this equation, that would just make the left side negative y. And then we try to resolve it to like the other equation. So if you divide by a negative, that actually flips all the signs on the other side as well. So if it's not the original after you've made the left side look like the original, then this is a fail, which makes sense. This does not fold as a match on top and bottom over the x-axis. And then the y-axis symmetry test, you change x to negative x. So this one will be a little bit more interesting. So we'd have negative x squared minus 3 times negative x minus 40. We work out the signs. Negative times negative would actually be positive x squared, but this is also negative times negative, so that's plus 3x and then minus 40. It looks closer to the original, but you're still messing up that sign in the middle, so this is also a fail. Too far down. And then the last one we need to do is we need to check to see if the origin test passed. So I'm going to do that one over here, running out of room. In origin, x changes to negative x and y changes to negative y. So that'd be negative y equals negative x squared minus 3 times negative x plus, minus 40. Has to be copied in correctly. So this would be negative y, negative squared would be a positive, so that's x squared, a plus 3x, and a minus 40. You have to divide everything by negative 1 to get y to look like the original, so that makes that negative x squared, negative 3x, and plus 40. So again, this one does not look like the original equation, so it's a fail. Now remember, I told you on your test, you're not going to have to do the symmetry test. It's good to know what they are because they actually relate to even and odd functions, which is something we cover a little bit later. But you'll have a picture in front of you, and you just have to tell me what type of folding symmetry it has. And then we need to do D. So do a table of values first. Find our x and y intercepts. This one will be our y-intercept. This will be our x-intercept. So if I plug in 0 for x, this is 2y squared minus 4. I'd add the 4 over, divide by 2, and then take a square root. So this actually ends up being plus or minus. So I'm going to rewrite this. This actually means we have 2 y-intercepts, negative square root of 2 and positive square root of 2. If we plug in 0 for the y, we're going to get just one x-intercept, which is negative 4. So negative 4 comma 0. This should be enough points, but if you want, you can try another point. You could plug in 1 for y. I'd actually plug in for y because this is solved in terms of x. So that'd be 2 times 1 squared minus 4. So that would be 2 minus 4, that's just negative 2. So negative 2 comma 1. Okay, let's plug what we know in. So we have negative 4, 0. That's an x-intercept. Square root of 2 is about 1.4, so we have a positive 1. So that would be 0 square root of 2. And down here we would have another one at 0, negative square root of 2. And then my extra point was negative 2, positive 1. So you can see, instead of having the x squared, when you have the y squared, you end up having a parabola on its side. And I can clearly see that this one has y-axis symmetry, but I want the test to prove that. So my test for symmetry, for x-axis, you plug in a negative y, so that would be x equals 2 times negative y squared minus 4. You square the negative, so that makes it back positive. So notice this is exactly the original equation. If that happens, it's a pass. So this has x-axis symmetry. For y-axis symmetry, we change the x to a negative, so that'd be negative x equals 2y squared minus 4. We try to make it turn back into a positive x by dividing everything by a negative, and that flips all the signs on the other side as well. So that's a fail. And for origin, we try to put both negative and x and y both in. So negative x equals 2 times negative y squared minus 4. I'm going to square this first. That turns it back into a positive y. This is still negative x, and then I would have to change it by dividing by negative 1. So again, once you get the left side to match, if the right side does not also match, it is a fail. So it does not have that symmetry. And that makes sense. The only symmetry I see here is the x-axis. Okay, let's do E. E is an x cubed function, so again we're going to try to find our intercepts. So if I plug in 0 for x, that is y equals 1/2 times 0 cubed, so that's just 0, which means that's also going to be my intercept for the other part, because 0, 0 would be the same intercept. So I'm going to need some other points. So maybe -2 and 2. I'm choosing 2 and -2 instead of 1 and -1 because I see a denominator of 2 here. I want to make sure whatever I plug in will divide out that fraction. So let's plug those in. This would be 1/2 -2 cubed. -2 cubed is -8. Half of that is -4. And 1/2 of 2 cubed is +8. So 1/2 of that is +4. Plot our points. So 0, 0 is the only intercept that we have. 2, 4, and -2, -4. It looks like a line, but it's actually deceptive. It's not. You might need to plot other points. Anytime you have x cubed, you kind of get a parabola that has decided to go in different directions. So one side of the parabola is going up, but the other side looks like it's going down. That's kind of what happens with x cubed. Now this one should have origin symmetry, so we do need to show that because it's been folded over twice. So the x-axis test, it should fail. So that's when you plug in -y. And if you try to solve that over, you get -1/2 x cubed, so that is not the original on the right side. It also fails the y-axis test because you're plugging in -x. And that makes that negative cubed would actually still be negative, so that's -1/2 x cubed, so that's also a fail. The way this is origin is because you're going to get two negatives that are going to cancel each other out. So with origin symmetry, you plug in a -y and a -x. You get a negative over here. You also get a negative over here because you're cubing that negative. So negative divided by negative goes back to both sides being positive, which is a pass. So that means this one has origin symmetry, which I can see from the picture. And then one of my classes graphed this one and the other one didn't, so I'm just going to regraph it just so everybody has it. Square roots are a little bit harder because you cannot have an imaginary, so we don't want no imaginary numbers because you're on a real number line, not an imaginary number line. So we have to force this radical right here to stay positive or 0 because square root of 0 is okay. So what we do is we set the inside greater than or equal to 0 and we solve by adding or subtracting whatever we need to do. So on your table, you don't just put in random numbers. You follow this, what we call restricted domain. So we plug in 4, maybe 5, 6, 7, 8. I may not like all these numbers, but I'm going to try some. So square root of 4 minus 4 would be square root of 0, which is just 0. 5 minus 4 would be square root of 1, which is just 1. I don't think I'm going to use 6 because that gives me a square root of 2, which is not a nice number. And same thing happens with 7. You get square root of 3, not a nice number. But square root of 8 minus 4 is square root of 4, which is just 2. So that works. So if we plot this, 4, 0, 5, 1, and 8, 2, you'll notice this doesn't have any symmetries. I'm not going to do the test because we've already kind of exhausted that. And like I said, you're not going to be made to do the test. Algebraically, you just have to see it from the picture. So it doesn't fold over the x-axis. There's no mirror down here. There's no mirror over here on the other side of the y-axis, and there's no mirror down here. So if there's no mirror image of that piece of this quadrant anywhere else, it doesn't have any of the symmetries. And that's the end of this section.